I'm assuming that you guys are hearing me good. And we are now at the next chapter. Note that you got the quiz that you have by the end of, by midnight tonight. Okay. There's 2 questions, like I said before. You have one on simple circuits and one that's going to require KVL and KCL with the dependent source. Okay, let's move on to the next chapter. And what we want to do here is that I briefly talked about the direction of where we're going here. And what you're seeing here is that we're now in chapter 3, where it's known as the methods of analysis. And what we're doing here is that we're going to use KCL and KVL with maximum efficiency. As you learn it in physics 4B, it's not very efficient at all. I'm going to show you some techniques that, like I said, some people find actually pleasurable in solving circuit problems. Like that's what they're going to do Friday night or Saturday night instead of go out. So what you're finding here is that node analysis uses KCL to calculate these node voltages. And then a voltage is differences in node voltages. Mesh analysis uses KVLs and then it converts them into currents. And it turns out that currents between 2 loops turns out to be differences in loop currents. So we're going to start off with node analysis just because it seems to make a little bit more sense. And this is what we know about node analysis here. We're going to start off with independent current sources. Why? It's just easier. And then we're going to jump into voltage sources by adding them. And you're going to see that it changes things. And it creates these things called supernodes. And then later on, we're going to add dependent sources, which then kicks it up a notch. There's no doubt about it. Okay, so here we go. We're going to start with node analysis with current sources only. And what do I mean by a node? Well, what I mean by a node voltage is that it's a potential. Voltage is a potential difference. So every time you have a circuit, you clearly have to have a ground because of the power supply. So what you're finding here is that how I define my ground is actually arbitrary. And what I mean by arbitrary is that it doesn't have to be in any one particular location. And what I mean by that, it could be in, any location that you want. And what we're going to do here is that we'll try to show you that, in general, it's not super important of where you place the ground. It's essentially that, you have that arbitrary. Sometimes there's an obvious choice and sometimes there's not an obvious choice. And so because of the ground existence, we really are going to need to calculate n-1 node voltages. And that's really the thing here. So here we go. Node analysis with current sources only. So we're going to use node analysis. To get to node analysis, what I'm going to do here is that I'm going to use KCL. So let's go do this here. So what I'm going to do here is I'm going to set up a circuit where I'm going to apply KCL to every single node. And then I'm going to replace all the currents using Ohm's law. And I'm going to convert everything into voltages. So here's my circuit here. So here's my example circuit. So if I look at my example circuit, let me draw a current source. With 2 resistors. And then I'm going to have a resistor as a bridge. And then I'm going to have a second current source. And this time that current source is in the opposite direction. And it looks something like this. So I'm going to label these resistors. So I'm going to call this R2, R3, R1. And then I'm going to have 2 sources, S1 and S2. And then I'll call this resistor R4. So the first thing that I'm going to do here is I'm going to determine the number of nodes. So if I do that, you could see that I got a node up here. I got a node right here. And then I have a third node down here at the bottom. So there's only 3 nodes in the circuit. So what this tells me here is that I have 3 nodes, but there must be a ground in the circuit if I'm talking about a voltage. So this black one here, I'm going to call the ground. So here's my ground, and the ground means 0 voltage. So instead of 3 nodes, I have 2 nodes. So it's 3 minus 1 because that's my reference node. So what you're seeing here is that I have 2 unknown node voltages. Now remember, node voltage is a potential. So that means here that this node I'm going to call, the green one I'm going to call node VA, and the red one I'm going to call node VB. Okay? So now what I'm going to do here is that you can see here that what this is telling me is that I have 2 unknown voltages here. So my goal is to solve, right? So our goal is to determine these node voltages. And what are these node voltages? According to what we said here, they're VA and VB. So the only way I can do that is that I have to have 2 equations. So how do I get these equations? So the first thing that you want to do here is that now you want to pick current directions. So the question is, which directions are the current going to go? Well, it looks to me just, in some naive way, that if I look at the current source I1, it looks like maybe the current's going to be going down like this. And because that's R1, I'm going to be imaginative in my notation and call that I1. Then I have this current coming here across I3. Then it goes like this. And if I look at R2, I'm going to say that that's the direction of the current. So you can see I'm just arbitrarily. And then I get to R4 and I'm going to go, well, I'm going to pick some direction. And there's R4 right there. Has that current. So I've picked my current directions. So I picked my current directions and I define polarities. Oh, that's not right. Polarities. That means I'm going to come up here just for right now. Typically, I don't do that. But look what I'm going to do. That means that that's got to be plus minus. That has to be plus minus. That has to be plus minus. And that has to be plus minus. That's what I mean by my polarity right there. So the direction of the current then tells me that. So then the next thing what I'm going to do here is that I'm going to apply KCL to each unknown node voltage. And convert currents into voltages. Let me be careful. Node voltages. Okay? So let's go do that. So you could see here that I have node A. So, okay, so let's do this. So I'm going to focus on node A. Actually, I'm going to just do this here. So here I go. So for node A, it's not looking very good. Look at the green here. How many currents are coming in? So I'm essentially saying what's coming in must be what's coming out. So that tells me that the current coming in, of course, has to be I source 1. The currents coming out is 1, 3, and 4. So I'm going to go I1, I3, I4. Now remember, I have voltages now. So if I look at the current I1, you could see that there's a voltage drop across R1. What is it? It's got to be VA minus the ground. So now I'm going to convert it using Ohm's law. So this should be VA minus 0 divided by R1. That's Ohm's law right there, right? So if that's the case, what you're seeing now is that I'm going to go and do the rest for the other resistor. Look at I3. I3 is exactly the same. It's VA minus 0 divided by I3. And look at R4. R4 tells me when I look at that current, it's going from plus to minus, so it should be what? Look at this node right here. What is that? That's VA. Look at this node. That's VB. So it should be VA minus VB R4. And this has to be I source 2. So what you see here, I generated an equation here. And this equation is for node A. So what am I going to do now? I'm going to do the exact same thing for node B.
Carlos?
Okay?
Carlos,
Yeah.
is that supposed to be I source 1?
Yeah, I'm just seeing if you guys are paying attention. Okay, that's good. Now let me move on. Let me go to node B here. Thanks for the help, Tim. Here I go. Node B. So if I look at node B, again, I'm going to look at the currents coming in and the currents coming out. Note that the only current coming into node B is I4. And then I have the currents going out. So then this should be what? I4 must be I source 2 plus current I2. So then I convert these again. Now, what I'm going to do here is that look at that I2. I'm really going to write I4 minus I2, and I'm going to keep the I source on the right side here. Is that what I really want to do here? Yes. So let's check this out. So if I do the algebra here, you know what? Let's just leave it the way it is because I want to show you what the book is going to do here. So I4, we already calculated I4, so we know that's VA, VB over R4. Then I have I source 2, and then I have I2 now. I2, you could see that has to be VB minus 0 over R2. So if you look at this thing, I now have a second equation. So what I want to do here is that I want to clean it up a little bit. And what I mean by cleaning it up is note that I have one equation, right? And I have a second equation. So what's customary is that the current sources are constants. So we can sort of like shove them to the other side here. And so what I want you to see here is that if you follow the textbook problem strategies, you get these two equations. So now what that means here is that you now have two equations, right? Equations 1 and equations 2, and you have two unknowns. In this case, it's VA, VB. So I can solve for B, VA in one, and I could solve it, put it into the other one. Does that seem pretty standard here? That looks, you know. But what I want you to pay attention to is that if this is what the textbook, let me show you a Carlos trick, which is not in the textbooks. And the only reason why I even talk about this is that for me, I study mathematics. So I'm always looking for tricks to move things faster along the way. Let me show you my trick here. This is what I call Carlos's method. The other one is the textbook. Now let's look at this first equation right here. You could see that I have variables VA and VB. So let's write that out. So what I'm going to do here is that I'm going to take this equation, I'm going to bring it down so you could see that I'm not changing anything, right? Here's this equation right here. But what I will do is I'll take the box out because I don't want the box. But this is really the equation right here. Now what I'm going to do here is, look what I'm going to do here. I'm going to collect like terms. So if you follow the books process, you're not putting things into like terms. But now I'm going to put them into like terms here. So I'm going to collect all the A's and all the B's. So if I look at this, I'm going to get R1, R3, R4, VA, and then look at the VB here. VB is 1 over R4, VB, and then I have plus I source 1. Now, look what's interesting about this. Let me go get the circuit and bring it back down. So I'm going to come and highlight the circuit, and I want to bring it back down. My question is this here. So what I'm going to do here is I'm going to get rid of all of the currents. Okay, I'm going to get rid of all of the currents here now. Oops. So I'm going to get rid of all of the currents because we don't care about the currents. We only care about the voltages. Now, what we really did, and I should have really been a little bit more careful here, is that I'm going to move this down just a little bit, and I'm going to say this. What are we talking about? We're talking about node A. Okay, so focus on node A. Look what's interesting about node A. Note that resistors 1, 2, and 3, 1, 3, and 4 are connected to node A. So if I look at node A, I got 1, 3, and 4. They're connected to it. But what about resistor 4 here? You could see that resistors connected between two nodes. It's connected between A and it's connected to node B. So what you're seeing here is that these resistors are connected to node A. This guy is a mutual resistor between two nodes, A and B. Let's look at node B here. If you look at node B, what am I seeing here? That means I'm going to focus on that node right there. So my question is, how many resistors are connected to node B? There's 2 of them. There's 2 and 4. How many mutual resistors are connected between A and B? Well, there's only R4. So remember that. Now, what I'm going to go do here is I'm going to go get the Book's method now. Here's the Book's equation right here. So I'm going to come back down here, and I'm not trying to change anything, right? That's the Book's method right here. So what I'm going to do now is that I'm going to do what I did before. What did I do before? I said, let's collect like terms. So all I'm doing here is I'm going to collect like terms. And if I do that, look what I get. There is a resistor A, right? So if I look at A, I'm saying that excuse me, not resistor A. I have node B, so I focus on node B. So if I collect terms for node B, look what I got to do here. I'm going to take VB, this VB, and I'm going to take it to the other side. So I'm going to get R2, R4, VB, and then look at the A here. If I bring the A to the other side, I get this. That current source, I'm going to bring to the other side, so I get minus I source of 2. And so what you're seeing here is that, let's go look at the circuit here. Check this out. By putting it into like terms, I look at the node VB and I say, look at that, I got R2 and R4. In other words, these are all the resistors connected to node B. And now look at what happens here. This guy is what? Here's a mutual resistor between the two nodes. So it looks like I could actually come in and I could not do the books method, because the book method requires you to do what? It doesn't put it into proper matrix form, as I would say. You have to do additional steps to actually do that. But if you recognize the nodes, what resistor is connected to which node, you could get it into proper equation form. But there's a couple of things that we should note here. So check this out. Look at the plus sign for the source on the right-hand side. The plus sign, if I look at what's happening to the current source, look at the current source right here. That current source is doing what? It's flowing into the node. So the plus sign says that the source flows into the node. So it's a plus sign. Check it out over here. Now look at the source. If you look at the source here, I source 2, note that the current source is not going into node B, it's going out of the node. So look, if it's going out, there's a negative sign. So this tells us here that the source flows out of the node. So in my opinion, this form is far superior. Why? It's already in the right equation form now. So when I go and I compare what the textbook does, which is these two equations, versus Carlos's method that puts the equations immediately into solving form, well, this just saves you algebra. And let me ask you this question. What happens if you have 10 nodes in a circuit? If you have 10 nodes in a circuit, that means you have 9 equations that you got to solve. Would you rather have 9 equations that you manipulate? Or would you rather have 9 equations that are already in proper form? So my response to that is that you'd probably want it in proper form right away. And as Isaac says, it's matrix time, baby. Oh yeah, you're gonna get really good at matrix calculations on your calculator. So let me go summarize Carlos's method, okay? So here I go. I'm gonna use Carlos methods because it's just easier for setup. So I'm gonna call this node analysis with current sources only. A la Carlos, right? Here we go. So what do I do here? Step one. What am I going to do? I'm going to choose a reference. Reference node voltage. In other words, you're going to choose your 0 volting. Then label all nodes. And determine the number of node equations. In other words, you're going to have n nodes, right? This is the total number of nodes. And then you're going to go -1. Why? Because that's the ground. We already know what the ground is. And so what that tells you then is that this then gives you the number of unknown nodes, right? So I have n-1 nodes here. So I have a number of unknown nodes, and that should be equal to the number of node equations. Then I go to step 2. Then what I do here is that I apply the node equation. To each unknown node. So what do I do here? Now, the language is, so there's a language here that we should talk about. There's some language here. If we write R like this, this is called, of course, resistance. But 1 over R is not known as resistance, it's known as conductances. It's a conductance value. So here we go.
Carlos, question.
Yeah.
What if we, what's the number of equations if we have multiple known nodes? Like if we have a ground and say we know this is 12 volts.
Well, then that goes to the section where we have to start talking with of including voltages into node analysis, and that's not what I want to do right now. I would just want to make sure, right? I just want to make sure that we do the simple stuff first. But you're right; it would reduce the number of known node voltages then, right? If you know one of them's 12, then that's got to reduce the number of equations. So then what we do here is that it's the sum of conductances connected to node 1, which I typically call V1, and then you multiply that times V1. And then you keep doing this, and then you got to deal with the mutual ones now. So then you have the sum of mutual conductances. And then you could have multiple mutual conductances, and then you get plus or minus I of the current source. That's the node equation right there. So there's some sign convention here. So the sign convention is this here. If you have a current source flowing into the node, then you write plus I source. So on the right-hand side, you're going to put the plus sign. If you have a current source flowing out of the node, then on the right side, you write minus I source. And then what you do here is that in step 3, what you do here is that now you solve for the node volt solve for all the node voltages. Using matrix techniques, using a calculator. So if you have a calculator that does matrix techniques, you should use it. Since we're online, there's probably other online calculators. If we were in a classroom, you'd have to get a calculator. By the way, a good calculator is about 150 bucks if you buy it brand new, if you go to Costco. Which one do I really like? I like the 89, because when we get into phasor calculations, which are complex matrix calculations, the 89 really rocks. But it's expensive. But if you go on eBay, I think I was on eBay a little bit earlier in the week, I found some that were for 40 bucks that were a little bit older. And there's, but now that we're online, am I okay you using an online calculator? Yeah. Yep. Or as Isaac says here, you can write it off on taxes. Okay, so that's what you do here. So you gotta be able to solve systems of equations. And you know what? In my old website, I had a whole bunch of links that showed you how to use like the 89, 83, 84. If you YouTube it, God, there's so many damn good ones that, there's a lot of people that want to show you how good they are at using their calculators on YouTube. So you could use those sites here. So I'm going to let you look at those things here, but let's go do this. Okay. So what I want to do is I want to go look at an example. So let me grab my example and let's go do it. Oh my, I have the wrong example. Let me go look at this thing here. I thought I had my example here. Let me make sure that I'm looking at what I'm supposed to be looking at. So here we go. Let's go look at a simple example. And the example that I want to look at is this guy right here. Let me grab it. So I'm going to start off with this example right here. So what I want to do here is that this circuit provides problems here. Okay. And one of the things that we want to do here is that circuits with kilo ohm resistors always produce milliamp currents. Circuits with ohm resistors always produce amp currents. So the first thing that you want to look at is look at this circuit here. See how the sources are milliamps? So what you're seeing here is that this circuit mixes up ohms with milliamp sources. So it becomes very, very, very painful to deal with this circuit here. So here's the trick here now. So the trick here is to convert all resistors into kilo ohm values. In other words, when I look at the 100 ohm, I'm really going to write this as 1.1 kilo ohms. The 200 ohms, I'm going to write this as 0.2 kilo ohms. And then when I go to calculate my voltages, what you're going to find here is that the voltages are always going to be in volts. Okay, so then what this does here is that all voltage calculations will automatically be in volts. Why? Because we know if I multiply a kilo ohm resistor times a milliamp, you could see that these guys are going to cancel out and give you 1. And so that means here that the unit of this guy here is going to be in volts. So what I'm going to do here is that the very first thing I'm going to do here is that I'm going to convert all of my resistors into this guy here. So let's check this out. It goes like this. So my job here is that I have to, so you must convert the circuit into proper units. So here I go. I'm going to redraw my circuit. So what does my circuit look like? Well, I got a current source. And this is a 4 milliamp. And then I have my resistor, which is 0.1 K. I have my other one, which is a 0.2 K. And then I have my 1 milliamp. And then I just keep going along until I convert everything. So I actually have to bring this down a little bit because I have one more resistor. So then if I look at my next resistor here, it's going to be right here. And it looks like this. But wait a minute. Aren't we calculating voltages with node analysis? The answer is yes, we are. So what I need to do here is that I'm going to do a further simplification here. So there's an additional I'm going to drop all kilo and milli prefixes. Just drop them because we already agreed on this here. We know that they're kilo and they're milli. So if you drop them, look how nice the circuit looks like now. But we got to be aware of what's actually happening. So I really have, my circuit really looks like this now. So I have my current sources. Oh, there's a resistor here. So this is 0.1, this is 0.2, and this is 0.1. So if you look at this circuit, this is a much cleaner circuit than the other circuit. I don't have to deal with kili, I don't have to deal with milli, and so I don't have to put those into my calculator. So now I'm going to count, I'm going to do the counting now. So this is my circuit now. This is the circuit I want to solve. Okay, so here I go. So what am I going to do? Let's go through the steps now. Step one is what? Do the counting. So the question is, how many nodes? Well, let's draw them in. So the first node, I'm going to call this my first node right here. Then I have my second node. Then I have a third node. And then finally, I have a fourth node. And what I'm going to do here is that I'm going to define my ground. So I'm going to do the counting. So I'm going to count my nodes. So the number of nodes in this case is what? 4. So I'm going to pick my black one here. This is arbitrary. I could pick any one. So I'm going to call that my 0 one. So I really have 3 unknown node voltages. So in this case, I'm going to label them. I'm going to call this V1, V2, V3. So what are my unknown? These are my 3. So this means here I need 3 equations for my 3 unknowns. Okay, so this implies here that we need 3 node equations to solve this circuit. So let's go look at it. So here I go, step 2. Now I'm going to apply the node equation to each node. So here I go. So I'm going to start off with node 1. Let's focus on node 1. Look at that. How many resistors are connected to the red node? I have 1, 2. So here I go. So I got 0.1, 0.1. That's how many resistors are connected to node 1. Question, how many mutual resistors are connected to node 1? Well, look at the one between the red and the green. So what you're seeing here is that V2 is connected to that. So look what I'm going to do. Now it's minus the mutual one. So in this case, it's going to be 0.1 times V2. And note, there's this red one and the blue one connected to node 3. So what you're seeing here is that guy's going to be 0.1 V3. So you're seeing here is that this is connected to V1 and that these guys are the mutual ones. And then I asked the question about the source now. How many sources are flowing into the red node? And you could see that there's only one. It's the current source is flowing into the node. So what am I going to do? I'm going to come in, I'm going to put +4. Look at that. No kilo-ohm resistors. There's no milliamps anywhere, but this guarantees that I'm going to get volts when I punch this into my calculator. Let's go to node 2. So if I go to node 2, then I'm going to go, how many resistors are connected to the green node? I see that there's 1, 2, the 0.1 and the 0.2. So here I go. So I'm going to go 0.1, 0.2. The sum of the conductances connected to node 2. Then I look at the mutuals. There's one connected to V1. There's one connected to V3. So then I'm going to go, there's one connected to V1. So I put a minus, and then there's one connected to V2. or excuse me, V3. And that's 0.02. And then I look at that green one and I say, how many current sources are flowing in or out? And you could see that the 4 is flowing out. So on my right side, look what I'm going to put. -4, because it's flowing out. So this guy, because it flows in, this guy, because it flows out. Now, one more node. Node 3. If you look at node 3, let's look at that. It's the blue node. So how many resistors are connected to the nodes here? I got 1, 2, 3. 3 resistors connected to V3. So here I go. So I got 0.1, 0.2, 0.2. So the sum of the conductance is connected to what? Node 3. Then I come over here and I say, what are the mutual ones? Well, look at that. The 0.1 is connected to V1. The 0.2 is connected to V2. And look at that. The 0.2 is connected to ground. So I have 3 resistors here. So let's go put those here. So I got 0.1 connected to V1, 0.2 connected to V2, and then look at that, 0.2 connected to what? 0 volts. So that means I don't even have to consider the one connected to the ground because it's automatically 0. And then I ask, what about the current sources? Check out the current sources. Look at the blue. Are there any current sources connected to the blue? There's one. It's flowing where? Out. So therefore, I come in and I write -1. And again, that's the sign because it does what? It flows out of the node. So those are my node equations. So now what I'm going to do here is that I'm going to come in and I need to put this into matrix form. So here I go. So what you're going to see here is that I now want to put these 3 node equations into matrix form for easy grading and putting into calculator. So that means here, every term that's V1, I'm going to set it up so it goes like this here. So now I'm going to have my terms that are V1, V2, V3, and then I'm going to have my constant sources here. In this case, it's going to be the current sources. So let's look at the first equation. Well, note it's already in that form. So I'm going to go and I'm going to write it. So I'm going to go, so in this, the first equation, it's going to be 0.1, 0.1 times V1. There's a second term here, and that's 0.1 V2. There's a third term, 0.1 V3. And then this current source we already saw was +4. Right? So it's just this equation right here. Now I'm going to go to the second equation. It's 0.1 V1. Then I look at 2, and you could see that's got to be, it's got to be 0.1, 0.2. And then this last term is then going to be, should be a minus here. You know what? I'm going to put the minus sign outside of this thing because I want the minus out there. And then this guy's going to be 0. Let's see, 0.2 V3, and then I'll get minus 4. And then if I do the third equation, it's going to look like what? Well, you could see if I move a little bit faster now, this is going to be terms that looks like this. And then on this side, I get minus 1. So now I've put it into the proper form. And then what I'm going to do here is that next, I'm going to put into matrix form. So matrix form essentially says what? I take all the V1s and I put it into a matrix. So look at that. All these terms right here are my V1 terms. All these two terms are my V2 terms. All these terms right here are my V3s. So I start writing them down. So when I put them into my calculator, I actually don't try to simplify them. Right? That's all my V1 terms. And then I get all my V2 terms. Right? Here's my V2 terms. And then I'm going to get all my V3 terms. And then if I just keep moving up, I'm going to get minus 0.02. And then I'm going to get minus 0.1. And then I call that my matrix. And then that's V1, V2, V3. And then I put in my current source values. And my current source values are going to be 4, minus 1. So I'm going to have 4, minus 1. This is what you have to show me. Okay? So when I say you got to put it into matrix form, that means you got to show me this matrix. So you must show me this matrix. And then we have what's called matrix magic. You punch this into your calculator, you punch this into whatever it is that you're going to use matrix calculations for, and then you get values for them. So then you punch out and you tell me what these node voltages are. So your job is to give me the matrix and just spit out the answer. We're using matrix calculations as what? As a way of doing what? Using it to calculate numbers. That's what we have right there. So let me go get the circuit here. So this is my circuit right here. Now I'm going to bring this down below. So what this tells me is that it tells me that I have a circuit that looks like this. Right? And I'm going to clean this up a little bit. So what does this tell me here? So V1 is really equal to what? It's equal to minus 0.1 volts. V2 is minus 0.2 volts. And V3, you could see here, is going to be minus 0.4 volts here. So I now know what all the node voltage is here. So then the question that we're asking here, what is the power of the 1 amp source. In other words, what's the power of this guy? We know that that must be the voltage of the 1 amp source times the current of the 1 amp source. Clearly, we know what the current is. So look at the current here. How is the current flowing? Well, when I look at the current source, this is what you're seeing. So you can see here is that this is ground, which is 0 volts. This node up here, according to our picture, this is minus 0.4 volts. So note that minus 0.4 volts represents what? A low, and this represents a high. So the current is entering the lower voltage, going to a higher voltage. So this means here, since the current is doing this, this source is then what? Active. So what's the voltage of this guy? So we know immediately that we have a negative sign because it's going from the low to the high. So then it's the voltage difference across this. And we could see that the voltage difference across this is going to be what? 0.4 volts. The current is going to be 1 amp. So what's going to be the power? Let's be careful now. It's going to be 1 times 0.04. But wait a minute. These are kilo ohm resistors. These are milliamp sources. So look what I got to do. I have to come in by hand and go, what? This is a 0.04 milliwatt power source. So the power of the 1 amp source then is this guy right here. I now have calculated this guy.
Carlos?
Yeah.
Quick question. So I thought when we did away with the kilo ohm and milliamps, that was built into the voltages that we got. When
Yeah,
we go
the
to
voltages.
calculate,
So
when we go to
note that
calculate
that means that
power,
yeah, but power for sources has to be the voltage times the current.
and so the current, we still have to put the milliamp.
It's still
So that's
milliamps.
Oh, okay. Got
So
it.
here, I mean, you, and that's where you're getting the milliamp
Cool. Thank you.
or the milliwatt, excuse me. Okay. That's how you use node analysis to solve these problems here. So what I'm going to do now is I'm going to look at node analysis, but this time I'm going to look at it with voltage sources now. So now I'm going to look at node analysis with voltage sources. Okay. So here I go. So when you use node analysis with voltage sources, it turns out that the location of the voltage source in the circuit tells us what we got to do here. So when applying node analysis to circuits with voltage sources, the location of the voltage source tells us how, or tells us, how we modify the node equations. And it turns out that there are two possible locations. So what are they? One, you can have a voltage source connected to the ground. That's one possibility. Or you can have a voltage source not connected to the ground. And it turns out that where that guy is at tells us how we modify node analysis. So let's look at an example circuit. To show you what we mean by this here. So the first thing that I want to do here is that I want to consider this circuit right here. So I have a 10 volt with an 8 volt voltage source like this. So let's say that this is a 10 ohm, 10 ohm, 10 ohm like this. So what we want to do here is that we want to do our regular node analysis here when we start to look at this thing here. But before we do that, we need to do the usual counting here. So the first thing that we do here is that we have to put a ground someplace because we always need that. So then check this out. I'm going to put the ground here down at the bottom. And by doing that, what you're seeing here is that I have nodes here, right? Let's look at this node. So if I look at the first node right here, and then I have a second node, and then I have a third node. So the first thing that I want you to think about is that look at the 10. So if you look at this thing here, what we're seeing here is that if we do our counting, right? So step one says, let's do the numbers. So what you're seeing here is that there are what? There are 4 nodes, 1 reference. So that tells us that there are now 3 nodes that we would be thinking about. But wait a minute. Look what's going on. There are 2 voltage sources, one that's connected to the ground and one that's not connected to the ground. So the question is, what do those sources actually do to the circuit here? So we notice that there are 2 voltage sources in the circuit now. How do they affect the circuit? That's the question that we're really trying to answer here. So the first thing that we should do here is that let's focus on the first one here. And the first one, we're going to focus on the 10 volt source connected to the ground. Connected to the ground. So when you look at this thing, that blue node, right? This implies here that the blue node must be 10 volts. So when I come over here and I look at this guy, that guy must be 10 volts. So what this tells us here is that we can immediately see here that a voltage source connected to the ground reduces the number of node voltages to calculate, right? It reduces the number. So what we're seeing here is that we had 3 nodes, but we know one of these now because that's that voltage source right here. This is the voltage source connected to ground. So what you're seeing here is that we now really only have 2 unknown node voltages. That's what that 10-volt source actually did here. But you know what? I'm going to come and steal this guy here. I'm going to paste this guy right here. Right? That's what that guy is actually doing to us. So now the question is, what about the 8-volt source now? So now we want to go to this guy here, and this is the 8-volt source not connected to ground. So what does this guy do here? This voltage source not connected to ground, and the way I'm going to do this here is that I'm going to come in and I'm going to put some labels on this. So I'm going to call this node A, and I'm going to call that node B here. Typically, I would have labeled all of the nodes. And what you're seeing here is that you could see that a voltage source not connected to the ground really puts conditions on VA and VB here. So what you find here is that this source sets up a special situation. That requires care. With the node equations. So why does it do that? So what you're finding here is that VA and VB are not independent of each other. Here is that VA and VB are not independent of each other. Without a voltage source, they're completely independent. But with a voltage source, they're dependent upon each other. And what I mean by that is that look what happens. If the source is 8 volts, what do I mean by 8-volt source? It means it's the difference between, look at VA, it's the positive sign. Look at VB, it's the negative sign. It's the difference between A minus B here. In essence, if I look at VA, it looks something like this. So if we know VB, we immediately know VA. So I really it's really one unknown variable, not two, which is a little bit strange here. And what we say here is that here's what the care is here. So because VA, VB are now dependent on each other, we call this dependency a super node. And so the way we draw this guy here to indicate a super node is that we do the following thing here. We come in and we draw a dashed line to show you that there's a dependence between these two. So we come in here and we draw a dashed line like this, and this is customary. And this guy is what we call the supernode. And we use dashed enclosed loops, a dashed enclosed loop. And that signifies that these two nodes are not independent, but they're connected to each other here. So what we're doing here is that, notice, we've reduced the number of required unknown node voltages. And what I mean by that is that previous to the supernode, it was VA and VB. But this tells me here, though, if I know VB, I automatically know what VA is. So instead of knowing VA and VB, we only need, let's say, VB, or I could have said VA. We only need one variable, right? We only need one of them, not two of them. So what we say then is that the number of unknown node voltages is then what? We started off with 1, 2, 3, right? We started off with 4. So we had one reference. So then we went to 3 nodes. Then we subtracted 1 because this was the one what? Connected to ground. And so now we're at 2 nodes. And then we had another one, another voltage source, which was not connected to ground. So this is saying that we only have one unknown node voltage. So the number of unknown node voltages is 1. But there's a condition here. But we have a special condition. And this is what I call a super condition. And I typically call this SC. And the super condition tells us how the voltage source connects the two node voltages. In our case, the supercondition is what? Well, we saw that VA minus VB was equal to 8 volts. So this guy is our so-called supercondition. So that's how we deal with voltage sources not connected to the ground. So what we got to do now is that we have to modify node analysis. So here we go. So the way we modify node analysis is it goes like this here. To include voltage sources. So the first step doesn't change. What it does here is that we count the number of nodes, right? So the number of node equations must be then the number of nodes, which is what we've done already, minus the number of voltage sources. Okay, that's the first thing that we got to do. We got to go do the counting. So we got to figure out how many equations we actually need. Now we get to step 2 here, is that we need to do here is that if a voltage source is not connected to the ground, we must write a super node equation. So we got to write a super node equation. So what is a super node equation? So a super node equation reads, it's the node equation for node 1 plus the node equation for node 2. So if I have a source, what I'm really doing here, you know what, I should have drawn a picture, which I didn't draw. How about if I move this slightly down so you can see what I'm talking about? So if I have a circuit that looks something like this here, and in between here, I have some source here. Let's say that this is V source, and this is node number 1, and this is node number 2. Then I'm going to come in here and I'm going to do my dashed line to connect those nodes. So then I focus on node 1. Now node 1 may have multiple branches connected to it. So I write one supernode equation here. So I write the node equation for V1. Then I write the node equation for V2. And this is what I call the supernode equation. And then for this guy, of course, then along these branches, I may have some source current here. So when you're looking at that, step 1 here is to count the number of nodes and subtract the number of sources. I then come in and I apply the supernode equation to the supernode. And then what I do next here is that I then come in and I must apply the super condition.
So we're relating this to a current source, even though it's a voltage source?
No, the voltage source tells you how to connect nodes 1 and 2. In one of these branches, I could have a current source that's flowing in. Or I could have another current source that's flowing out. So I have to account for the sources right in here. When we do an example, it might be clear. So this is a theoretical discussion so that we know how to sort of like write this down. But now you got to apply a supercondition. So that means if I look at my circuit here, note that V1 is positive. You know what? That might be a little bit hard to see. How about if I do it in this color? So V1 is the positive. So then if I apply a supercondition that says in this case, it's going to be what? It's going to be V1 minus V2. In this case, it's going to be V source. So this guy is my supercondition, which is my SC value. And so that's how we modify node analysis. So one of these equations is going to be a supernode equation, and then we'll just apply it that way. So you know what? God, I'm over time by a minute. Sorry about that. So I'm going to stop here. And I got to let you go because I got to go into Physics 4A right now. So I will see you guys either on Friday lab or next week on Monday. All right. I'll talk to you guys later.
Have a
Later
good one,
on.
Carlos.
Thanks, Carlos.
Yeah, you too.